Hello everyone, Jim Malis again. Let's talk a little bit more. Let's talk about chapter 15. Let's approach it. Let's talk, this is chapter 15 from the Physics 209 book, the Katz book, first edition. So calculus treatment. People not in my classes not using the calculus treatment, not in a calculus-based class, can still get a lot out of these 209 lectures. I hope that's the goal. I think you can get a lot out of it because a lot of times we're not really going into the calculus level. Other times we are going to the calculus level, and some people have background in it and stuff. But the conclusions that are drawn, I think, are good for everybody who's doing this. So we're going to talk about Bernoulli's equation eventually, but let's kind of work our way up to Bernoulli's equation. There are a few problems I'm looking to do for sure. 22, 24, 25, 68 from chapter 15 from the Katz book, first edition. I may try to do a couple other ones. Let's see how it goes. For sure those is what the goal is. Well, guys, I mean, they talk about a number of things before we get over to Bernoulli's equation. Let's talk about a lot of what they're doing. They talk about fluids in chapter 15. They talk about fluid flow. And usually fluid flow, you're talking about gases or liquids. Predominantly, this Bernoulli's equation is going to work best with liquids that you cannot compress by putting pressure on them. Or at least under normal circumstances, it's an incompressible fluid. A gas is a fluid, a liquid is a fluid. Fluids that are incompressible typically are liquids, or at least in normal circumstances, they're incompressible. You're not going to change their volume by putting pressure on them. Gases obviously are different than that. You can change their volume if you put a significant amount of pressure on them. If you put any kind of pressure on them, you can change their volume. So that doesn't happen under normal circumstances for liquids. So this equation works best when we're talking about liquids, and we're talking about liquids where there's no viscosity. There's no, on the sides of the container, on the sides of the pipes, there's no resistance to the flow of the fluid. There may be other kinds of things going on hampering the fluid. There may be a push on one side of the pipe and a push on the other side of the pipe, one way or another, and somehow one overcomes the other, and then there's the flow of fluid. Whatever. There's some sort of resistance to it, I guess you could say, in terms of maybe work being done one way and then work being done the opposite way, something like that happening. But for our purposes, there's no viscosity. It's an ideal incompressible fluid. The idea of this equation being to work like that, it works pretty good. It explains a lot of things. I haven't even written the equation yet, but when you do see the equation associated with this, it is really a manifestation of conservation of energy. It's really just a takeoff of conservation of energy, and you'll see that. We'll cross that bridge as we need to cross it. Let's kind of like work our way up to that point, I guess you could say. So when you do get Bernoulli's equation, it's going to work best with an ideal incompressible, usually that's liquid usually, right? Ideal incompressible fluid, and Bernoulli's equation works great. However, Bernoulli's equation has applications when you're talking about gases as well. Non-liquid fluids, gases in other words. It also has application there to some degree or another, and does get used. Again, the ideal is probably the incompressible fluids that we're talking about. Okay, so that's something to kind of think about. When you're talking about fluids, there's a few things we've already kind of touched upon. I went into Archimedes Principle earlier doing some sort of problems that we were doing, right? Let's kind of like derive, or at least kind of come close to deriving here. Again, they say Dr. Katz's book, in this chapter we will limit our study to incompressible fluids. Incompressibility is one of the properties of an ideal fluid. Therefore, much of what we study is a very good approximation to the behavior of real fluids. Because gases are in fact compressible, there are many gas behaviors that we cannot discuss here. Gas compression, however, is discussed in chapters 19 through 22, and we'll talk about that when we get to it. But there is some application. Even with gases, there's some application. There's a lot that they can't say. Obviously, Dr. Katz mentions that, but they do kind of, it gets discussed at some level. There's some application to it. Not as good as an ideal fluid. Not as good if you're dealing with Bernoulli's equation pertaining to an ideal fluid, and that pertains to liquids. Liquids that are ideal and incompressible. Well, basically, guys, they say a number of things. Let's talk about water, or let's talk about any kind of fluid that you go under and find out what's going on. First of all, pressure is a scalar. It is the magnitude of the force applied onto something divided by its surface area that is experiencing that force. Pressure is force divided by area. Okay, that's rather interesting. If you were to draw an imaginary cylinder, I guess you could say, and let me see how. This is not a real big deal that I'm even erasing this, but let me kind of give myself a little room, for lack of a better way to say it. Say you're saying this, and there is a depth, let's say, and there's a whole bunch of ways you could play this, actually, guys. Let's say this is the fluid right here. This is the top of it, and there's, fluid everywhere. And this is just an imaginary, hypothetical, so to speak, surface, closed surface. What is the pressure that's experienced right here on this area, A at the bottom? Well, the pressure in any fluid at any depth is equal on all sides. In other words, at a particular depth, the pressure is what it is, and it's kind of going in all directions. So if I'm a scuba diver 20 meters under the sea, 20 meters below the surface, I'm experiencing, on my underside, if I'm like just swimming horizontally, I guess, I'm experiencing a particular pressure everywhere on me, and on the sides as well. Now, the higher up you go, even just the thickness of my body, there's less pressure right above me than there is below me. Well, let's talk. Let's see what this actually means, what the pressure is. How about you just say something, the water weighs a particular amount, and we can play a whole bunch of games with this thing. Let's take this thing here, and let's, for the heck of it, let's extend it. Let's extend it even more. Let's kind of go here. Let's have it go up here too, whatever, from the whole depth, from depth 0 right here to depth, right here of y. So that's a depth of y, let's say, all the way down to there. What's going on here? Well, the fluid itself has a density rho. The brand new cylinder here that I've drawn here, all the way here to here, has a volume of this base area moved through a distance y, ay, or ah, the height h, whatever. That's the volume. Is it true, guys, that rho is the mass density of the fluid? The mass density times volume will give you the mass. The mass times g will give you the weight. The weight of that column weighs down right here on this area. The weight of that column weighs down on that area. How much area? Area A. So wait a minute. So you're telling me the pressure, and again, I don't want pressure in rho. Rho is the Greek letter for R. P is the Latin-based letter for P. The pressure is the force down there divided by the area. Rho is the volume. I'm sorry. Rho is the mass density. V is the volume. Mass density times volume is mass. Mass times G is the force. Over A. Wait a minute now. Didn't we say that the volume was A times Y? And there's your G. Divide by A. Again, the P's and the rho's look a lot alike. I'm trying to be careful here. That's a P, right? The A's cancel. That's rho YG or rho GY. The pressure at that depth, Y, is rho GY. I guess that makes sense. The further down you go into the water, the more pressure you're feeling on your ears and on your whole body in general. You can feel that pressure. That's for real. Notice it doesn't matter how big it doesn't matter how wide the cylinder is. Say, what happens, Malus, if you make the cylinder really wide? It's a lot more massive, isn't it? That imaginary column of water is much more massive if you make the cylinder much bigger. Well, the length is the same. But let's say you made the base area 10 times bigger. If I expanded this thing out to here, the base area, if I expanded this thing out to here, the base area is 10 times bigger. That means that's 10 times more volume. Yes. 10 times more volume means 10 times more mass. Agreed. 10 times more mass, mass times G, 10 times bigger mass means 10 times the force at the bottom. Agreed as well. Yes, but it's spread out over 10 times the area. So you might have, at the end of all that, you might have 10 times the volume. Right? But that came from 10 times the area. So you got 10 times the area times Y times G over 10 times the area. 10A and 10. Yeah, I know you have 10 times the mass, which means 10, in this new scenario, expand the base and make the base 10 times more massive than it was earlier. 10 times the base 10 times more massive, 10 times bigger. If the base is 10 times more area, it's 10 times more volume, it's 10 times more mass, it's 10 times more weight. Yes. 10 times more weight divided by 10 times the area, the 10s cancel. And what happens is you're back to square one. Rho GY. So it's going to be the same. Sure, yeah. Oh, wow, man, it's 10 times more mass, 10 times more weight. Yeah, divide it by 10 times the area. Yeah, there's 10 times the weight, but there's 10 times the area. Back to square one, ladies and gentlemen. That's not an issue. So that's a pretty big thing. It's a pretty big thing in the process here, guys. And then, where does Archimedes come into this thing? Archimedes was one of the first, if not the first, to be doing elements of calculus. Certainly among the first. When he was doing calculus, there was integration methods. I don't know the whole story, but he was definitely, in the Western world, frequently Archimedes, Gauss, and Newton get mentioned as the three greatest mathematicians, at least in the West. Been great mathematicians and great intellectuals everywhere, known and unknown. So that's, so always be aware of that. So, but at least in the West, they mention them quite a bit. What is going on here, man? So where's this Archimedes principle come into? I'm kind of putting the carriage in front of the horse, or I've already done that, in fact. We are looking at a situation. What is the buoyant force here? Well, I'm going to tell you something. if you're really deep in the water, there is a lot of force right here, but there's also a lot of force right there, and a lot of force the other way, and a lot of force the other way. And if there's a lot of ways to talk about this. Let me just, remember we're getting into that issue of the forest and the trees, and I don't want to mess you up either way with too much forest or too much trees. There's a lot of force going right this way, and there's a lot of force going right that way. There's less force when you get up here, and there's also less force when you get up there. And there's quite a bit less here, and quite a bit less there, and right here it's like really small. There's not much at all. Are you seeing something here, guys? Yeah, there's at particular depths, and this comes out in three-dimensional space. It's going everywhere on the cylinder, not doing anything to it, not making it move. The symmetry here means, yeah, he pushes hard this way, he pushes hard that way. Yeah, he pushes just as hard this way as that guy does this way. Same push, same amount of force this way as the force that way. Nobody's moving. It's all over the place. Same thing here. Same thing here. Etc., etc. Here's smaller. I mean, I can't really, it's small enough. But everybody's pushing with so much symmetry. It is always symmetric at a particular depth how the push is being manifested. Very strong push that way, same strength push that way, same strength push that way. On the other side of this thing, same push that way. So nobody's moving there. You go up a little higher, there's not as much push. Why is that? Because we talked about the pressure being rho gy. And as the y gets smaller, the pressure ain't as big, the force ain't as big. Because pressure is force over area. So that's that. Nothing going on over there. Yeah, there is kind of an interesting issue though. Let's there's a lot of ways we could go here. Let me come back to the original guy. Let's put him here. Let's put him here. Let's go right here, guys. Let's not worry about the others. Let's go over here. What's going on over here? Well, this is depth y. Let's call this guy depth y2 to come down. Let's call this guy depth y1. And this is still the A there. Well, wait a minute. Didn't we say the pressure, one of the premises is the pressure is equally distributed at a particular depth. It goes in all directions, and if you're at a particular depth, at that depth, the pressure is everywhere present. So it's not a vector, it's a scalar in that regard. It's everywhere present, and it's the same. It's the same everywhere it is. So if that's the case, there's two situations here. There is a delta P, a change in pressure, which is P2 minus P1, which is rho G Y2. That's the deep one. And rho G Y1, that's the shallow one. Let's see what we can say here about this whole thing now, how we want to actually talk about it. We talk about it a bit. We say rho G Y2 minus Y1. So what's going on here? Well, yeah, there's more pressure on the bottom because it's at a deeper depth than there is pressure on the top. That means there is a force, I guess you could say there's a force pushing down, and that's manifested in a number of ways. And there's a bigger force pushing up. This is F2, let's say. And this is F1. Yeah, F2 is bigger than F1. I mean, I'm looking at it. We'll say that's F1. And we'll say that is F2. Yeah, what does that mean? Well, there's a pushing war, and this guy wins it, which means what? If he's lighter than water, let me just say it like that in very generic terms, he's going to get fired upward. It's kind of like that beach ball we talked about earlier. There's going to be a buoyant force throwing it upward. Pretty fascinating stuff. That is pretty amazing stuff in that regard. So what you're doing is you're basically, what is going on here? Well, this right here, you could say this a bunch of ways. I guess you could say rho gy, that's P. What's the buoyant force going to be? The buoyant force, the resultant force is going to be delta P. Let's try to talk about this. There's a number of ways to do this, and I'm not necessarily looking to show the number of ways to do it. The delta P, the change in pressure, is going to be the change in the tug of war in force divided by area. Now, how does that work when it's not a pretty thing like that, like a cylinder? What if it's a beach ball? What if it's something else? You can break them up into individual volumes, individual columns, each column looking like a cylinder, or each column looking like a square column, looking like a column that has a square on the bottom for the base area, a square on the, or square or a rectangle, it doesn't matter. Square is a special kind of rectangle, but let's say square. Square might be a little easier to look at. But square is a special kind of rectangle. You could use a square base area and then build columns. And you just build a whole bunch of columns using the techniques of calculus, or at least the conceptualization of the calculus techniques, infinitesimal columns with square bases. And then say for each one of those, how is this pressure being manifested? And when you add them all together, you're coming out, you're coming out to a lot of stuff that's going on there. You're getting, let me see exactly what I want to say here, guys. I mean, there's a couple things I'd like to say about this. We can say, let me come back to the more elaborate argument of what's going on here. But you're basically doing, the change in pressure is going to be this, and that's, that in itself is very important. That already is a very important conclusion. So when you're trying to look at this stuff, let me talk some more. Then let me hook around about what I was talking about earlier. We know that delta P is rho g y2 minus y1 equals delta F. And you could almost say, I mean, don't hate me for this, guys. Delta F is, the resultant force is delta F. You can just call it F for the resultant force, or the buoyant force at that point. The delta F is the buoyant force, and it's this right here. And it's going to be, and that's just the delta F. That's the change, but it really is a delta F because there is a pushing battle going on, and we got to find out what's happening there. Multiply by A on each side. Put the FB right here. Maybe this will give you a little bit of a hint. FB equals rho g, the base area, times the difference in the depths. Well, wait a minute. Hold the phone here. If this all the way down to here is y2, and all the way down to here is y1. The difference between the two, that right there, y2 minus y1, is the height of the cylinder. Is the height of the cylinder. So FB equals this. FB equals rho G, and again, I multiplied by A on each side. Remember, I started up here, guys. I started up here. I had this guy right here, more or less started right here, more or less started right there, multiplied, more or less started right there, multiplied by A on each side, got this. And FB is FB. A y2 minus y1, the whole thing like that, that's H. FB equals rho G A H. Wait a minute. Base area times height is volume. The buoyant force is rho GV. The buoyant force is rho GV, or I think I write it like that, rho GV, or rho VG. I mean, it's the V and G. Rho times V is the mass density. G is the acceleration due to gravity. For the buoyant force. Yeah, it's completely believable. Completely believable, guys. So, I mean, it looks like this. And what does that mean? You know, is there an interpretation here somewhere? I mean, the buoyant force is rho VG, rho VG. Rho times V is the mass of the fluid. Yeah, it's not the mass of the cylinder. This is the big thing here, guys. Rho VG is the mass of the fluid that surrounds the cylinder. Rho V is the mass of the fluid. Rho V is the mass of the fluid that surrounds the cylinder. What does that mean? That means the amount of fluid displaced in terms of mass times G, in other words, the weight of the fluid displaced, is the amount of buoyant force that's being exerted on the cylinder. And the cylinder's got a different mass than that. So that's where it's coming from, a lot of that stuff. So you're saying force buoyant is rho of the fluid times G times volume of object, of the cylinder in this case. Pretty fascinating stuff. It's fascinating in a number of ways, really. Here, it doesn't get into the issue of depth. I know I talked about depth here. Hey, there's a depth here. What do you mean there's a depth? Well, there's a depth from here up here, all the way down to here. That's a depth of y2. From here all the way down to just here, that's a depth of y1. And then I got the difference between the two. And the difference between the two is what kind of made... The difference between the two was H. H could occur anywhere. H could occur at a depth of 10,000 meters in the sea. I mean, whatever, if it's that deep. I'm not an oceanographer, but it could occur at a depth of... It could occur at a depth of 5,000 meters, where this is all taking, roughly around at a 5,000 meter depth in the sea. Or it could occur at a depth of 10 meters in the sea. H is H. So this gets interesting. It's the volume of the object. It's the volume of the object. So there's something going on there that it'll come out just right, and you're adding all these little volumes, and then you get the buoyant force. This gets you out of the woods because you don't need to know. You don't need to know specifically all the depths. You need to know the differences in depths. The differences in depths are individual elements of the volume. There's a base area and there's a height. What's the height? It's the difference between two depths. How deep are we talking about? 5,000 meter deep in the Mariana Trench, or 10 meters deep somewhere in Lake Michigan or something, or whatever, or some other in the sea. Let's say we use salt water's got a different density. It's going to be the same material though, same fluid. We can deal with salt water. We could be at a depth of 5,000 meters in depth to talk about the buoyant force at that particular point. Or we could be at a depth of 10 meters rather than 5,000 meters. You don't really need to know the depth. You need to know the volume. And the volume, remember I was telling you earlier, I could build square columns, each with a very, very small square geometric configuration on the bottom and the top of area dA, if we're going to use calculus, dA, delta A, and make delta A smaller and smaller and smaller. Call it dA, differential element of area, on the bottom. And then there's a height, and whatever the height is. And I can keep playing games with these columns, guys, and if I add rho fluid don't change, G don't change, V of the object changes, and I can just add all the objects together. I can add all of these together, and it becomes the volume. See, the rho of the fluid ain't changing. G ain't changing, and I can do it with one of my square columns, V1, the other one of my square columns, V2, in volume. Square columns, volume, V1, V2. V3 plus ... plus V sub n, and V sub n could be very, very many of them. Add all these together, that's just the volume of the object. Even if it's not a pretty geometric figure, it can be really, really bizarre looking. This right here, bam, all these anomalous volumes, but I've constructed them from summation. Well, they're not anomalous, they're columns. I can make them columns with base area, dA, whatever, very small. They're square columns. Each base area, the area of the base of each column is a square, very, very small. And it could be a very long column, but the base area is very small. Infinitesimal in size. Add them in the limit, add a very, 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 very big number of them. That's just the volume of the object. No matter how bizarre the object looks, it'll still get you that. That's pretty interesting. It'll still get you that. Okay, so there's a lot here. There's Archimedes' principle for you. Here's Archimedes' principle for you again. Just written a little, a little louder, so to speak, I guess you could say. So what's going on here? What is going on here? Well, yeah, I mean, so look, there's a long story short on this whole thing. The buoyant force is the weight of the fluid displaced, period. The buoyant force is the weight of fluid displaced. So the buoyant force is the weight of the fluid displaced, and that's what's the weight of the fluid displaced? Give me the density of the fluid. Give me the density of the fluid multiplied by the volume of the object. Give me the density of the fluid in which the object is immersed, and tell me the amount of fluid that has been displaced. The amount of fluid that's been displaced is the volume of the object that has displaced the fluid. The volume of the object times the density of the fluid will tell you the mass of the fluid that's been displaced, times G will tell you the weight of the fluid that's been displaced, and that's the buoyant force. And that's the weight of fluid displaced. Archimedes discovered this. He also discovered how water, like we got into the tub, took a bath or whatever, and the water rose. He figured the volume of his body that was immersed displaced in that exact same amount of water. So the volume of his body displacing the water, the amount of displaced water was the volume of his body, and he was able to draw various conclusions. And there's, the Evrika, he said, Evrika. That's where the word eureka, I say translated in English. I found it. He said he ran through the streets of Syracuse, Sicily, without any clothes, saying, I found it. He discovered this. So, and he was actually able to, you could find out that an actual king had actually been cheated by a jeweler. The jeweler lost his head, having cheated the king, because he was able to determine what should have been the correct density, what should have been the right weight for that given volume. And again, all that kind of plays a role within Archimedes' principle. Okay, so that's Archimedes' principle. That's also, as far as, let's kind of hook around a little bit. Forgive me, guys. Let's kind of come back to what got us to Archimedes' principle, and that is we said that the pressure due to the weight of the fluid, right? The pressure due to the weight of the fluid was equal to rho g y. Sometimes they put an h there for the depth. Different books do different things, you guys. Let me just make sure I'm speaking reasonably here, I guess you could say. Different things get said. Yeah, that's true. I want to add one more thing, guys. What about the atmospheric pressure on the outside? You got to remember, guys, there's an atmosphere. There's an atmosphere that's got weight. It doesn't have, I don't know, it's a question, this idea of a tremendous amount of weight or not. Maybe there's not a tremendous amount of pressure, but it's a significant amount of pressure. Why is there not a tremendous amount of pressure? Because it doesn't weigh as much as gold. It doesn't weigh as much as mercury for the same volume. It doesn't weigh as much as water for the same, but there is pressure. There is air. Air has mass, and there's a gravitational field pulling the air down. It's pressing on us, and it makes it possible for us to breathe. When we change the pressure, when we create a vacuum in our lungs, air rushes in, and we're able to breathe. So it's there. So if there's an initial pressure going on, plus pressure associated with depth, we get to here. I think they call that Pascal's principle. I just don't see it written here. That's the odd thing here. Let me see here. Yeah, there's yes and no. I mean, yeah, it's essentially going in that direction. It's Pascal's principle in some sense. And the book goes into it too, as I have. So you look at this. Here's Pascal's principle, kind of in a nutshell. Here's Pascal's principle in a nutshell. Here's Archimedes' principle in a nutshell. This is an explanation of it, and this is where it goes like that. and we talk about it here. Where rho is the rho of the fluid, and V is the volume of the object. The object displaces a particular amount of fluid. So, that's kind of where we're going here, guys. So you got Archimedes' principle, Pascal's principle. Before we work our way to Bernoulli's principle, let's talk about the continuity equation for flow of a fluid. It's pretty straightforward stuff. It helps us out. Let's see what we got. What's this continuity equation? What's all this continuity stuff they're talking about, guys? Well, I'll tell you what. Let's see exactly how I want to do this. Look, there is a system, some sort of a system where fluid is allowed to flow. It's an ideal fluid, incompressible, so it's liquid. We already mentioned they can kind of sort of get away with talking about gases in terms of Bernoulli's equation to some extent. Some of the principles can get used. Some of what gets said can be kind of, sort of. But again, the best way to look at it, we shouldn't get too enthusiastic on that part of it. It's got to, the best way is ideal fluid. That's a liquid, incompressible, and that's the way to kind of look at it. There's aspects of, what we're talking about with fluid dynamics. Certainly you can bring gases into it as well. Okay, so it's kind of out there. All right, this, I already don't like the pipe I drew, but okay, I drew it, let's live with it. Let's say there's a lot of symmetry here in certain parts of the tube, but not in the tube throughout its entire structure. If there is a flow of ideal fluid here, and there is a flow also of ideal fluid here, what's going on? Well, the pipe is really big. It starts way over there, guys. Somewhere way over there the pipe starts. This is horizontal. It's not climbing, it's not falling, whatever. Even if it was, you know what? It doesn't even matter. It doesn't even matter if it was or not. For right now, let's say it's horizontal, but it doesn't really matter. If the pipe is real big and there's flow going through here, if this is flowing, whatever amount of fluid comes in is the same amount of fluid that comes out. There is no way anything is flowing unless it's flowing everywhere. What am I talking about? I'm talking about if, let's say there's 100 kilograms of fluid, 100 kilograms of fluid going through here. 100 kilograms of fluid going through here every second. What do you mean? I mean right here, 100 kilograms cross over this cross-sectional area. So this cross-sectional area right here, we'll call them A1. And I'm going to say past A1, and it flows past here as well. That's A2. 100 kilograms, bam, fly across this thing every second. Really? Yes. Well, yeah, if this thing's incompressible, it can't hit a log jam, you guys, and not flow. If it hits a place where it's not allowed to flow, there ain't going to be 100 kilograms coming into this thing every second. If 100 kilograms goes through here, I guarantee you 100 kilograms is going to flow out of here as well. That's what they mean by the continuity equation. There's no, whatever goes into the pipe comes out of the pipe. I don't care what the pipe is shaped like. Whatever goes into the pipe comes out of the pipe. Okay. That's kind of interesting because here it is. It's crossing over here, 100 kilograms, right? So in 1 second, bam, it crossed over. Here's 100 kilograms for you in 1 second. In 1 second. Over here, there's 100 kilograms for you. Make it a little bigger here so we kind of, guys, it's not going to be any work of art here, but we're doing this. Really? Each individual particle, there's a lot of there's a lot of things can be said here, guys, and for right now, I'm not going to get too fancy. On average, each particle coming in there is coming in pretty fast. Yeah? It's coming out even faster. Look, you've got to have a mass M coming in there every second. A lot of times they write it like this. Q means volume flow rate. Then they put a volume in there. Oh, well, okay. Well, we're not gonna sweat that right now. We're not gonna go there yet. That's mass M. This is also mass M. You know what? This guy right here at this edge, will travel all the way to here in 1 second. This guy right here will travel all the way to here in 1 second. And this guy right here will travel all the way to here in 1 second. All these, the cross-sectional area of particles, here will travel all the way to here in 1 second. The cross-sectional area of particles here will travel here in 1 second. The cross-sectional area here of particles will travel here in 1 second. Now, I don't know. We can debate that. There's stuff that goes on when we talk about electricity, drift speed, and all this other stuff. There's probably a connection here as well. But for our purposes, let's refrain from all judgment on that. Let's just kind of get a gut feeling for how fast a cross-sectional area of particles are moving. Effectively, how fast they're moving. Whether it's some kind of chain reaction sort of thing, which is what happens with electricity, or something else. For right now, for our gut feeling, saying, right here, this cross-sectional area will go from here to there in 1 second. Over here, this cross-sectional area will go from here to the start. The start will go from here to here in 1 second. This will go from here to here in 1 second. You get it. The middle will go to another middle in 1 second. Same argument over there for our purposes. This is L2. This, same mass, M, is L1. Yeah, guys, what goes in has to come out. If you're making another, no, I don't agree with you. 100 kilograms goes in 1 second. I agree with that. But Malus at the end, only 50 kilograms comes out in 1 second. No way. The pipe won't let that happen. If it flows, everybody flows the same. The fact that it is contracted here, ladies and gentlemen, means it will be slowed down. I mean, the flow rate, whatever. There's issues here that come into play. I'd have to look at it. But look, more ideally would be for this big thing right here to be the same big thing all the way across. And it'd still be 100 kilograms per second. Or maybe more. If it was like that, it might be 200 kilograms per second. The fact that you did this, you've hampered things a bit. That hampering, however, is already accounted for in the final scenario and in the initial scenario. You may not get as much in there because of the configuration. Whatever you do get in there, however, is going to come out. Very important. Very important. So what are they saying? Losing chalk left and right, you guys. So we got this right here. They're equal to each other, right? We got to talk. If this is the case, in a time period t, mass divided by time equals mass divided by time regardless of location. Rho of the fluid times the volume equals rho of the fluid times the same volume. The volumes are the same. We got to talk a little bit. We got to definitely talk a little bit here. And this is T and this is T. Do you guys notice? And I don't think any great artist has anything to worry about with what I'm doing here, guys. This volume here is roughly the same as that volume there. Now we can argue this left and right, man. I mean, this isn't even realistic, to be honest with you, because this thing goes in three-dimensional space. It's a very broad area. This goes in three-dimensional space, and it's not a broad area. It's not, the cross-sectional area is not that big right here. Probably a better way, I just wrote it because it's easier maybe to, I don't know, maybe to look at. I mean, if it was somehow like a rectangular thing that had the same depth, this would be right. If it had the same depth, then yeah, you could say something like that. If it was a rectangular thing and it was just looks like a radiator or something like that, it wasn't a circle, that'd be a good drawing. Otherwise, it's maybe not a great idea to write it like that, because this is in the three-dimensional realm bigger. Right now, who cares? We're going to believe mass equals mass, and what does that mean? If mass equals mass, is it true that rho times volume equals mass? Well, rho times the same volume is the only way to get the same mass. If rho doesn't change, the volume's can't change. The volume flow rate is identical. The volume flow rate is identical for the mass to go. So what does that mean? Well, basically means this. Divide by rho on each side. You got rho V1 over T equals rho V2 over T, where big V is the volume coming in, that's equal to V1, and the volume coming out, which is V2. These are all volumes. These are all volumes. Okay, I agree with that, and they use Q sometimes for that. Can you say anything else? Yeah, I can. V1. V1, let's talk V1. Cross-sectional area A1 times L1 is V1. A1 times L1 is V1. Yeah, that's the same as V2. And V2 is A2 times L2. Yeah, I got another thing to ask. What is length divided by time? In time, 1 second, you went that far. L1 over T is small v1. L2 over T is small v2. what just happened here? What just happened here? L1 over T is small v1. L2 over T is small v2. And there you go. And that's the continuity equation. Again, not the greatest drawing in the world. I mean, this is like the first time I'm actually noticing this. You can kind of look at it this way and see. This only works if you had, let's say, something really narrow. The pipe had the same width. Let's say it was a rectangular type pipe, and it had the same width everywhere throughout, but there's different heights of it. And that accounts for different cross-sectional area. If that's the case, width times height, that'll give you a difference in the volume. And that's when this works. I don't know. I mean, more realistic would be to make this a lot smaller. At the end of all that song, and like something like that. You say, where are you coming from? Why are you getting that? Well, because it's also got broadness to it that was never accounted for. That frequently doesn't get mentioned, guys. We're not going to lose a whole lot of sleep on it. That don't mean a whole lot. However you want to look. The big thing is mass coming in is the same as mass coming out. The volume of fluid going in is equal to the volume of fluid going out. If that's the case, this is what goes in, this is what goes out. Absolutely true. These are volumes. And absolutely, and then at that point say, well, what is volume V1? Well, divide by rho on each side. Divide by rho on each side, you got V1 over V2. I'm sorry, you got V1 here, you got V2 here. And then what does that mean? Well, that means base area times L1, and this is base area times L2. That right there is speed. This right here is speed. And that's where you're getting, and that, as we said, guys, and that's where you're getting the A1 V1, the A2 V2 for the continuity equation. Okay. Bernoulli's equation is kind of a ripoff of the conservation of energy equation. We know that energy is conserved, and we kind of just deal with that a little bit, and we write it in a different manner. We write it kind of like as energy per unit volume. Energy per unit volume is energy density. Bernoulli's equation is a fancy way of writing energy density. You're taking energy and you're dividing it by volume, and you're getting Bernoulli's equation. Well, let's see what they're saying on that. Okay. See what we can say here regarding a lot of this stuff, you guys. We can look at this and say, well, okay, Bernoulli's equation, let me just write it out, and then we'll kind of come full circle around it. Okay, well, perhaps there is kind of a precursor. You look at this, it's kind of a precursor of what you're going to see. In other words, or at least it's in agreement with what I've said. Okay, so we said this, said all this. I ran out of room because I write so big, guys. But you see what I'm writing here, guys. We're saying that P1 plus 1/2 rho V1 squared plus rho GY1 equals P2 plus 1/2 rho V2 squared plus rho GY2. One more time. P is pressure in both instances. Rho is the density of the fluid. Same fluid in both instances, and rho is the density of the fluid. Forgive the fact that P and rho look alike, just watch out for it. Okay? P1 plus 1/2 rho V1 squared plus rho GY1 equals P2 plus 1/2 rho V2 squared plus rho GY2. Wow. This 1/2 rho V1 squared looks like 1/2 MV squared. This rho GY looks like MG. Ignore the rho for a second. In a place where you see rho, put an M. In a place where you see rho, put an M. 1/2 M V1 squared. 1/2 M V2 squared. In a place where you see a rho, put an M. MGY1. That's like MGH1. Put an M right here. MGY2. That's like MGH2. There's something going on here. The P, where's that coming from? Well, very much can be said. Let's take a look at it. We know that's the goal over there, guys, to your far right. We know, and the book does a great job as well, how they talk about this. Once again, I was a little too generous in the size of these, in the strictest sense. Because if it's a real big pipe, you guys, it's broad in 3 dimensions. If it's a big pipe, it's broad in 3 dimensions, so it's going to be a little different dynamic. We're not worried about that. We're assuming it's the same mass. The continuity equation is alive and well. Wait a minute. We just did this whole song and dance with the continuity. By the way, it doesn't matter that there's a climb. It doesn't matter that the fluid has to climb. I get it. The fluid climbs and then it falls down again and then it really climbs up real high and at the end it comes out at its source and you're able to water the garden. You're able to water the crops. True. Doesn't matter. All of that, it matters in the sense of what the flow rate's going to be, but the flow rate's going to be identical no matter what the configuration is. If this is an ideal incompressible fluid, if you got this thing flowing, it's very likely, given the energy source that you have, it ain't going to flow that well if it has to do a big climb. That's for sure. If it was going downhill, it would flow better. And it'd be the same flow going in as going out. Maybe in more ideal, if it's falling down or something like that, for a given amount of, maybe for a given amount of work that you do, hey man, I'm going to have this thing go downward, and there's a whole bunch of other things going on. Let's say the work that I do on the water to get this thing to go and everything else. Some very interesting problems, and we'll get into that. If not in this video, we'll get into some other things later in other videos. But for our purposes, if the stuff is flowing downward, if I can get a whole lot of fluid flowing into this thing, the fact that gravity's helping it and whatever, there's going to be a flow rate. If I'm trying with the amount of work I got to do to try to get this thing to go the other way, it's going to be tough. It's going to be tough. If I'm trying to get this thing to climb, the flow rate is going to be hampered. That's okay. That hampered flow rate is identical at the source as it is after the big climb. It's already accounted for. So the continuity equation is alive and well. Remember we said A1V1 equals A2V2. It's already accounted for. Don't think, oh, what are you talking about? It's having to climb up. It's going to be less. That's already accounted for. It's going to be less all the way around. It's going to be less going in terms of volume flow rate, and it's still going to be less coming out. In other words, but it's going to be the same amount. It ain't going to be ideal. It ain't going to be much, but it's going to be the same amount of not much. The not much coming in and the not much coming out are the same. Okay. And we're kind of coming right here to this. Okay, so I mean, you're looking at something like this. We've talked about this. I want to make some arguments here. So in a period of time, and we're looking at base areas. Now the mathematics, though the drawings, if you really want to be strict, the drawing ain't good. The mathematics is right on the mark though, and that's what we're going to go with. The drawing's just a guide, so for our purposes, we're okay. If you really wanted to be more meticulous, I'd probably cut this thing a sliver that big to the left of my hand, maybe a sliver that big, depending on how big this thing is. I don't, how that whole thing works. Depending on how the pipe looks as well, guys. I guess my way out is I never told you what the pipe looked like. It could have been shaped like a wall, and like a tall wall or a short wall, and the sides, the sideways is the same throughout. It's just the height of it looks different. How likely is that? Not likely, but it can be done. So you look at this thing and you're saying, okay, well, energy is conserved somehow. There is work. Okay, I just want to make sure I want to kind of talk with you about this. There is work being done right here. Work is W. It's force times distance, right? A force acting through a distance is work. There's a lot we can say, but let's say that for now. I'm not going to worry about the dot product or anything like that. Work is force times distance. Fair enough to me. There is work W1. There is work W1 being done right here. Work W1 being done right here. There is work W2 being done in the opposite direction. What is it? I don't know what it is. There's something. There's something hampering the flow. Don't know. Maybe there's something else. There's some other kind of work going on. Let's hypothetically say it's going on the other direction. Well, I know there's going to be a fight there, and you better come out of it on top. If you're going to have this thing flow upward, W1 and W2, there better be, things better be working as far as we need to do this. Tell you what I'm going to do. I'm going to say it again. There's W1 amount of work this way pushing the fluid. There's W2 amount of work fighting that flow. Could be friction, could be something, whatever. I want to say something. W1 minus W2, saying W1 pretty much wins it. How does that all work? Well, he wins it in a bunch of ways. One's going to be more than the other to make this thing happen, and what has to happen? This mass at the horizontal level, this amount of mass at the horizontal level at a height y1 has how much total energy? You guys remember, there's kind of that basic premise. Energy initially present in the mechanical system equals energy finally present in the mechanical system. Assuming it's a closed system and no extra business happened. So E1 equals EF. Let's take a look, guys. I'm going to say W1 minus W2. W1 minus W2, W1 wins. By how much? W1 minus W2. What's going on? Well, what's going on is there is initially present Well, there's a lot going on here. What happened? What happened for this to happen? In time t seconds, the mass flowed this much. So V2 is L2 over T in time t seconds. That's V2. In time t seconds, this guy went this way. In t seconds, L1 amount of fluid flows. That's V1. Okay, so what, you might say? Well, I'm going to say something happened here. And here's what I'm going to say. This amount of fluid climbed up to here. How high did it climb? Well, it climbed Y2 minus Y1. So Y2 minus Y1 is the amount of climb of an amount, we'll call this amount of mass right here, ladies and gentlemen. We'll call that amount of mass M. We'll call this amount of mass M. It's the same amount of mass. And I'm saying you did this gymnastics of Y1 being strong, you did this gymnastics of W1 being stronger than W2 by how much? Well, W1 minus W2. That's how much net work was done. W1 minus W2 is the net amount of work that was done. What was accomplished? What was accomplished was you picked this thing up. You took the mass M and you picked it up to here. From a height of Y1, you picked it up to a height of Y2. Force times distance, there you go, you got him. Then, what happened here? Yeah, the kinetic energy changed, guys. This guy was going faster. I got to say, just my gut feeling, V1 is faster. V1 right here, associated with this guy, is faster than V2, associated with that guy. What does that mean? Well, it means that, yeah, you gained potential energy, but you lost kinetic energy. V2 ain't as big as V1. And this describes what just happened. We're certainly not done, but it describes a lot. Tell you what I'm going to do. Let's take, okay guys, I want to use chalk that can't keep track of my chalk sometimes, guys. It's different kinds of chalk I like to use to make sure this works okay for you guys. Let us multiply mg all the way across to these two. Distribute mg. Then distribute the 1/2 m across to these two. Then get all the subscripts with 1 in them over to one side, and then add the subscript with 2 in it right here over to the other side. You end up getting, and let's just see how they wrote it. I'll write it like that. I'll put the 1/2. Different places write different things. I think I've seen this written in different ways. I typically put put the potential energy in front. That's not a big deal. That's nothing. I mean, that's no big deal. Let's talk. You got this. So mg times a negative y1 is negative mg y1. Add a positive mg y1 on each side. 1/2 m times negative v1 squared is negative 1/2 m v1 squared. Add a positive 1/2 m v1 squared. Add a positive w sub 2 on each side. Go 1/2 I'm sorry, forgive me. Go mg times y2, leave it alone, because it's already on the side you want it to be on. It's already on the right side, so to speak, and it is on the right side, literally and figuratively. Then go 1/2 m That's important. That's important. It's starting to look like this. Tell you what I'm going to do. Didn't we say, let me kind of cut to the chase on this one, guys, a little bit. Didn't we say that work is force times distance? So W1 is a force times the distance D1. W2 is a force times the distance D2. Tell you what, let's make it a little easier. The D1, you guys, there's nothing wrong with the D1 I put on there. Nothing wrong at all. But let's stay consistent with what they wrote. There's so many ways to write this. Again, I had other videos on this. I think I've already hit this, you guys. I don't know what the quality of the video was in the past. These are much better. Force times distance, huh? Yeah, true. Tell you what I'm going to do. Do you agree, despite any debates we want to have on the aesthetics of this, the mathematics dictates, the physics dictates what we said earlier in the lecture, and that was that the volume flow rate is identical throughout the hydraulic system here, throughout the hydraulics, throughout the piping here, throughout the pipes. The volume flow rate is identical everywhere throughout the pipe for an ideal fluid. For an ideal incompressible fluid, the volume flow rate is identical. The volume flow rate is identical everywhere throughout the pipe. What does that mean? That means volume, V1 over here, down there, is identical to volume V2. Does that look familiar? Yeah. That means A1, L1, for that 1 second of flow, that for 1 second, L1 distance is covered in the sub 1 location. For 1 second, L1 of distance is covered. In location 1, L1 distance is covered in amount T. In amount T, L1 distance is covered in location 1. In location 2, L2 distance is covered in the same time T. Yeah, they're equal. We got to talk. If two things are equal, if you divide by the same thing, you get the same answer. Be very careful. We did say the volume flow rate is V, ladies and gentlemen. It's V. V1 equals V2. All of those are volume. All of them are volume. So, see what we can say here, guys. Okay, great, so what? I mean, so V1 equals V2 equals V. I could not divide by V2 on the right-hand side and then divide by V1 on the left-hand side and then claim it's still an equation. This was an equation based on the song and dance that I was trying to deliver earlier. That's an equation. I agree with that. But if you divide by something on this side, you have to divide by the exact same something on that side. Volume V1 equals volume V2. Equals volume. So they are identical. So you can leave it there or not leave it there. That's not a big deal. It's not a big deal. What is the big deal? The big deal is all right, we saw what the conclusion is. That conclusion ain't changing, guys. Go F1, L1. Over V, or over V1. Go M over V, GY1. This should start to kind of shed some light on the conclusions we're claiming earlier before we proved it. Okay, running out of room again. You got to forgive me on that one, guys. You got F2, L2 over V plus, here we go, V goes into here, V goes into there. You know where I'm going. Okay. When I give myself more room, I run out of room, I guess, right? Can we talk? Isn't volume base area times length? I'm not going to do it for all those. I don't need to do it for all those. But it's true. In all instances, it's true. Base area times length. All right. L1 and L1 cancel. And you got F over A, which is pressure. F1 over A1 is pressure. You divided by volume, and you end up getting pressure. Mass divided by volume, so that's pressure. We'll call it P1. F1 divided by A1 is P1. M over V is rho. M over V is rho. Now it's starting to look like something. That's pressure. This is rho GY2. This is rho GY2. This is 1/2 rho V2 squared. That's it. You divided by volume. It's mathematically valid. I guess if I have an equation as I had way up here, and then I manipulated it, I had an equation way up here, and the equation way up here can be written such as this, above my hands, written such as this, above my hands, then divide by V on each side, it'll work. Yes, but when you divide by V, you are finding the energy density. This is true, but the amount of energy, this is a true equation in the right circumstances. This is definitely a true equation. This is definitely a true equation in the right circumstances. absolutely the true equation. The thing is, if the volume is huge, a tremendous amount of work needs to be done if you're going to supply the water supply. If you're going to supply water to Chicago for their needs, this equation holds, but the amount of work required is huge. If you're going to supply water just to a building or to a small house, the equation still holds. Not as much work is required to get that water to come over there. But to get it to come over and go to wherever it needs to go, to a huge city like Chicago, a huge amount of volume is needed. It's a bigger answer. We'll get more into this. Get more into this definitely in some other circumstance. There's some stuff that kind of comes to mind. But anyway, so there's Bernoulli's equation. There's kind of a nutshell of what goes. There's other stuff in here as well, guys, but this is some stuff that will give us the strength to get through some things that we want to get through. So let's see. And then we can always come back. Let's see what time permits. You know, what I'm allowed to do. Not today, but maybe another time I can look at some stuff. Hopefully soon when people are looking at this, I'll also have the opportunity to talk to people in person. That might not happen anytime soon as this is being done in the fall of 2020 as I'm doing this particular video, okay? But later on, the content of it will be very useful in any kind of circumstance. Be nice if we could augment it with being person to person. It's probably it's the best way to teach as far as I'm concerned. Okay, there it is, guys. You got it. It's up here. You're looking at it. Let me make sure you can see it well. Yeah, it looks fine. Looks fine. So let's take a look at these four, and we'll see if there's, we'll see what we can say beyond that. And I'll try at some other point to maybe bring up Bernoulli's equation. There's some great, great things to look at. So I also have it done for you actually in Canvas. I have, I think, a really fascinating Bernoulli's problem that I saw somewhere that is solved for you guys. I think it's one of the practice exams that were for the in-person exams that would take place, that were not able to take place at this juncture as I'm saying this, right? Given the circumstances that have transpired. But so there's, throughout Canvas, guys, I've got examples of this everywhere. So whether I get a chance to come back at this or not, you do have Canvas. And there's a lot more things in Canvas than I'm ever going to have a chance to film myself doing. Probably ever have a chance to do it in person, even with you guys. There's just a lot of stuff I tried to put on there. But it's there for you for your personal enrichment. Look at it at your convenience if you wish to do so. Okay, so let's see what this is right here. And probably I think I'll stick to these four. Let's see what, at least for now, so for this particular video. But again, it's all about the equations. Being able to use the equations, guys, that's oftentimes easier said than done, obviously. All right, let's see what we got. Let's see what we can say. For problem number 22, and this is Archimedes Principle in play on this one. For problem number 22, a spherical submersible, 2 meters in radius, armed with multiple cameras, descends underwater in a region of the Atlantic Ocean known for shipwrecks and finds its first shipwreck at a depth of 1.75 times 10 to the 3 meters. In other words, 1,750 meters depth it finds its shipwreck. Seawater has a density of 1.03 times 10 to the 3 kilograms per cubic meter. That's 1,030 kilograms per cubic meter. And the air pressure at the ocean surface is 1.013 times 10 to the 5th pascals. What is the absolute pressure at the depth of the shipwreck? That's A. B. What is the buoyant force on the submersible at the depth of the shipwreck. Okay, pretty classic problem. Good problem to look at. They give us some data. It's good to have it at hand. We remember we have it at our disposal, how to find volumes in different circumstances and stuff. So let's have a look here. Okay. Number of ways to look here, guys, on so much of this stuff. You can use H for the depth as well. You've seen me kind of play the game here on this. Let's see what we can say here. They're telling us the pressure, P sub naught, sometimes they call it P atmosphere. P atmospheric pressure, it's P naught, that's 1.013 times 10 to the 5th pascals. They're telling us for this object used for the exploration has a radius of 2 meters. The depth to which it went was 1.75 times 10 to the 3rd meters. That's 1,750 meters. The row of the sea, or of the ocean, call it the sea, that's all in front of us. The hardest part of this thing, guys, to get this thing together is P equals P0 plus rho GH. Rho GY, rho G delta Y, either that's not going to be an issue for us. Let's find out what the pressure is here, guys. The rest is the mathematics straight out applied. Basic stuff, let's do it right. Let's not be careless when we do it. That's 10 to the 5th. That's 101,300 plus, and here we go. Rho is this. G is this in the Katz book. Those of you looking in on this from another course, they might be using just 9.8. Kind of follow, the convention that they're doing in a particular book. I guess you could say is the best way to do it. Again, the application, the mathematics should not be an issue. We've got 17,783,825 pascals. They round that off a bit. It's 17. They go to about 17,800,000. 17,800,000, which is this. And there we go. What's the buoyant force? Buoyant force is FB. Rho of the sea, GV. Yeah, we've been there. We've done this. This is what we were talking about the whole time up to this point, right? We were talking about this. The buoyant force associated with Archimedes Principle. How about rho of the sea? G, the volume is 4/3 pi r cubed. Should be pretty straight, guys. Make sure units are agreeing. If the units agree, you should be fine. Here's 4/3. Here's pi. Got to deal with it, right? And there it is. $338,598.34 newtons. You know me, I take the stuff as far out as I can with that. It's, I don't round anything off and put it in there. I try to get around the issues of the significant figures, guys. I don't try to call you on that. You've got enough math and enough physics to try to figure out here. And we had even looked at other, I don't even want to go down that road. You've got more than enough to deal with, right? So right now, let's go here. I wrote this down. They managed to, and that's fine what they're doing. I just want to make sure the rules are straight. If you go here, a little bit of a round off, 339,000. That's it. Let's go to 24. 24, an object in a fluid has a density, rho object is 1,755 kilograms per cubic meter. It is submerged in a fluid of density rho sub f. If acceleration is upward with a magnitude of g divided by 3, what is the density of the fluid? Ignore any drag force on the object. This is a great problem. Classic sort of, I guess you could say, for lack of a better way to say it, a classic aptitude type problem. You don't need to know a whole lot of physics, but you got to have a really logical look at what's happening here. They're telling me this object is in a fluid. The fluid has density rho sub f. It might be water, it might be mercury, it might be liquid gold, I don't know what it is. It's something. It's got a density rho sub f. The density of the object is 1,755. 1,755 kilograms per cubic meter. It's pretty dense. It's denser than water. And they're saying this thing goes upward. So it's already telling me the density of the fluid around it is more dense than the density of the object. If the density of the fluid and the density of the object are identical, nobody's moving. There's going to be no buoyant force. Take that back. There is a buoyant force, but there's not going to be a net acceleration upward or downward when that happens. So density of the fluid is going to be more than 1,755 kilograms per cubic meter. Let's figure this out. Let's look. Let's look at it. Let's put some of the numbers down and let's argue where we need to go. See here, guys. All right, so let's look at 24, you guys. For the life of me, guys, I thought I could have sworn I had more chalk up here than what I needed. Oh, there it is. All right. I'll put these in one place. Okay, what are they talking about, guys? Let's figure this out. I mean, they're saying basically here's a surface for you. I'm trying to put waves in it, I guess, right? But I don't know if that's a great idea. There's the mass of the object. The mass of the object's got mg. And the buoyant force is bigger. V is going to be the volume of the object. And we'll talk about that. Notice they didn't tell me the volume of the object. We just know that there's an object. If we know there's an object, ladies and gentlemen, we know that there's a volume associated with it. We're going to have to be careful here. V is the volume of the object. I'm going to have to say that. The rho of the object true, they told us that. They want you to find this, so they obviously did not tell you this. Density of fluid. They did tell me that the acceleration in terms of magnitude is as big as the acceleration due to gravity divided by 3. So they told us that. And at the end of the day, you got to get this under control. You have got to find this, given everything that they've told us. Got to find the density of the fluid. So, what's going on? What's going on is what's always going on. Force equals mass times acceleration. Mass times acceleration will be the unbalanced force that this thing is experiencing. I think I've made it clear. Perhaps I have, perhaps I haven't. That arrow is bigger than that arrow. Not incredibly obvious, but let's say it is. FB is bigger than mg. The buoyant force minus the pull down due to gravity, the difference between the two, is equal to this. This is really the engine that's going to operate the whole thing. You've got to be careful, though. MA is MA. The buoyant force is the density of the fluid times G times the volume of the object. Density of fluid times volume of the object, which displaces V amount of fluid. The V amount is the volume of the object. The volume of fluid displaced is equal to the volume of the object. This is the mass of the object. This is G. This is the mass of the object. It's the mass of the object, guys. It has to be the mass of the object. Look at it. There's the mass. Mass of what? The object. The object. Because the object is moving through the fluid. Not the fluid through the fluid. The object is moving through the fluid. See what I can do. Let's add mg on each side and factor out an m. Okay. G over 3. G over 3 is 1/3 G. G is 1G. One-third G plus 1G is 1 1/3 G is 4/3 G. Fascinating stuff, guys. It's one of those great, it's I guess you could say maybe, you can argue it a whole bunch of ways possibly. It's one of those great SAT type problems, or LSAT type problems, or GMAT type, or DAT, or any one of those standardized examinations. If it can tell you enough, can you actually work your way around it? It's a good aptitude type question where not incredibly complicated, but can you work your way around to what's happening? And there's other ones that are even better than this, certainly, but this isn't bad. If two things are equal, you guys, as you can see, you can divide by G on each side, and you got 4/3 m equals rho f times v. Divide by v on each side. Wait a minute now. If this is the mass of the object, and that's the volume of the object, that's rho of the object right there. Absolutely true. So what is that? Well, rho f is going to be 4/3 rho of the object um, 585, let me just do this. 2345, I'm thinking something like that. I'm just doing it in my head right now really quickly, guys, before I turn the page. Okay, they're saying this. I don't know if I agree with that, but I think it is true, actually. What happens is you can do this. You can go 3 into 1755, and it will go in 585 times. 585 times 4 is going to be, for some reason, I'm getting different, maybe a little different answer. I'm doing this kind of in my head here, guys. Maybe I shouldn't be. The 585 times 4, that's going to be 2340, 2360. How do I see here? I got the 585 times 4. Yeah, that makes perfect sense. That should be, that's the 2340. Yeah, that's right. It was on there. It was right. So what we have here is, at the end of all that, sorry guys, just trying to see if I can do the mental math. Sometimes I can, other times I cannot. But there it is. (2340) kilograms per cubic meter. We said it had to be more. It had to be more dense for that to work out, you guys. So that's 22, 24. Let's go to 25. (25) is saying a hollow copper with a density, a hollow copper spherical shell. It's a hollow copper spherical shell, rho sub Cu, that's for copper. A hollow copper spherical shell, the rho of that copper spherical shell is 8.92 times 10 to the third kilograms per cubic meters. Of mass, M equals 0.950 kilograms, floats on water with its entire volume below the surface. A and B, what is the radius of the sphere? What is the thickness of the shell wall? Another great aptitude type problem, I guess you could say, with something like this. All right, guys, for 25, Well, you saw it. Now, again, don't know how to say this. I mean, there's a number of ways this could be played, but strictly speaking, you want to be as precise as possible. Maybe you could argue, perhaps somebody could argue that, maybe there's another way to do this. I mean, perhaps, I can do some, there's an approximate way to do this and a very, very exact way to do this. And you want to stay with the very exact way to do it, I think is what you want to do. So let's take a look what they got here. Now, copper is pretty dense. How do I know it's pretty dense? Because water generally speaking, for the sake of argument here, let's just be approximate, depending if we're talking about fresh water or salt water or whatever. Water has a density roughly 1,000 kilograms per cubic meter. Copper has a density roughly 9 times that. That means for the same volume of copper, there is 9 times more mass present. In the same gravitational field, it's 9 times heavier. It's got a weight that is 9 times that. All right, so looking at this, you guys, this is a bit of a, let's see what we can say here. We're going to say it's a shell, aren't we? All right. If we're going to say that it's a shell, you want to be careful. You want to say a lot of stuff. Tell you what I'm going to do. I'll say R sub 0. Actually, R sub O I'm going to say. R sub O is the radius of the outer. The radius of the outer shell is R sub O. The radius of the inner shell is R sub inner. Okay. What does that mean? Well, that means the thickness is delta R. That's R sub O minus R sub I. So I'm looking at, this is one big part of the puzzle that's got to be looked at. That's got to make some sense. So, let's see what we can say here, guys. They are telling us that rho of copper, that's the scientific way to say it, rho sub copper is the mass of the copper that's present divided by the volume of its shell. We're not worried about the air that's enclosed, way inside, We're just worried about the copper itself. It's all copper. The air, we'll say it's negligible for us. So what does that mean? Well, they're telling us, they're telling us a number of things here, I guess you could say. They're telling us that the mass, the spherical shell, the mass is 0.950 kilograms. So let's talk. V of the shell multiplied by V shell on each side and you got this. V shell, they're telling us the mass of this thing, they told us this, guys. 0.950 kilograms is the mass of the shell. They told us that copper is 8,920 kilograms per every cubic meter. So from there, we're going to find out the volume that got us the 0.950 kilograms. Do the division, you're there. You got 1.065 times 10 to the negative 4 cubic meters. Okay, that helps. We got that. That's V of the shell. V of the sphere, and some of this I'll bypass this. You can look at my notes as well, guys. V of the sphere, the V sphere is the volume of the entire sphere. The mass of the water displaced is the rho of the water times G times the V of the sphere. We are told that the entire sphere, outside radius RO, the entire sphere displaces its entire volume of water exactly. And it's just below the surface. So it ain't going down, it ain't going up, and it's right below. So the mass of water that has been displaced, forgive me, the volume of the water that has been displaced, the volume of the water that has been displaced is equal to the volume of the outer sphere. There's two spheres, right? And there's a shell composed only of copper. And we're not caring about anything else. Everything else is a vacuum. So, if that's the case, mass of the water displaced. So let's see what we can say here, guys. Mass of water displaced, that's the amount of water displaced, times G is the buoyant force. And what is that? Well, the mass of the water displaced is the rho of water. What's the mass of the water displaced? It's the rho of water times G times the volume of the sphere. And that's equal to and this is the big thing. The mass of the copper, ladies and gentlemen, the mass of the copper times G is the weight of the copper sphere, the copper shell. The mass of the copper shell, times G is the weight of the copper shell. That weight of copper shell goes downward, and the buoyant force goes upward. So this is the buoyant force, the rho of the water times the volume of the spherical shell. Forgive me, no, I'm not going to say that. The volume of the sphere, the outside sphere. The volume of the big sphere, times the rho of water will tell you the mass of water that has been displaced, times G, that's the buoyant force. This buoyant force going upward is equal and opposite to the mass of copper times G going downward. The mass of copper times G does this, the buoyant force does that. So that's this, and that's that. And they're equal and opposite. It's a big part of this thing. It's a big part of what we're doing, guys. All right, well, okay, we said what we said. Is there a way to do this? Well, we are told that this guy, the mass of copper is 0.95 kilograms, and that's G. So we got 0.950 kilograms times G. That's this. That's what this guy is. The other one is rho of water. They didn't tell us what it was. Did it say it was the C or not? I guess we used 1,000. Then we'll use for rho of water. So this guy right here is this, and this guy right here is about to be what I'm about to do. Okay? Well, here we go. This is getting us closer, I guess. The V of the sphere Wow, that's pretty crazy. The V of the V of the sphere, let's divide by 1,000 G on each side. 0.950 G divided by 1,000 G V of the sphere is 0.950 divided by 1,000, which is 9.5. 0.950 divided by 1,000, which is 0.950 divided by 1,000, which is 9.5 times 10 to the negative 4 cubic meters. That's pretty significant. Not bad at all. So what are we going to say here? Well, I guess I can get the outer from this game right here, you guys. I mean, there's a lot you can do, and I don't know how you want me to play this thing. I mean, how do you want to go here? Let's do this. Let's make it easy. Do you agree that 4/3 pi hour, 4/3 pi hour, and I can't even talk now, guys. 4/3 pi r outer cubed is V of the sphere that I've been talking about this whole time. If you solve for r sub 0, how do you solve for r sub 0, man? Well, how about you multiply both sides by 3 and divide both sides by 4 pi. True. That's what r sub o cubed would be equal to this. Cube root both sides, and you get this. True. True. Now what? Just do what you know how to do. Go 3 times 9.5 times 10 to the negative 4. Let's have a look here. That's 3 times 9.5 times 10 to the negative 4. Divided by the product 4 pi, get an answer. So 3 times v sphere divided by the product 4 pi, get an answer. Cube root that answer, rather. I'm sorry. That's a cube root, guys. We're so used to using the square roots. It's got to be a cube root. Cube root the answer, and that'll be it. And that'll get you there. So it's 3 times 9.5 times 10 to the negative 4 divided by the product 4 pi. Cube root that quantity, and you get RO. And the outer radius of the sphere is 0.0610 meters. That's the outer radius. True. The question was, indeed, they gave you an easy way out on this one. 25A, what is the radius of the sphere? Well, they kind of, even that in its own right, I wish, what's the radius of the sphere to the very, very edge of the sphere? Well, actually, I take that back. The sphere is the sphere, guys. The sphere's got to be the entire object. The entire object is from the dead center all the way to the outer edge. So R sub 0, it makes sense. For 25A, what is the radius of the sphere? What is the radius? What is the radius, the outermost portion? What's the outermost radius of the sphere? Maybe a better way to put it. The outermost radius of the sphere is 0.0610 meters. Okay. What is the thickness of the shell wall? To find the thickness, I got to find Ri, and then I'm there. To find Ri, we got to figure this out. We can figure it out. This is the volume of the entire sphere. But what are we going to say here, guys? These were buoyant forces now. We got to make the mass of the... Remember now, the way we did this was... Got to figure out exactly what we're saying here now. We got to say, okay, well, if we go back to this guy and figure out the weight, we already know the mass of the copper. It's a very interesting problem. Let's just be careful about it. Let's be careful. We can do it. So we got A. A is what it is. And that was A right here, guys. How are you going to find the other one? I'll tell you the long story short, I guess you could say. I'll make the long story short. If you find out the total volume of the object, and be careful here. This is the volume of the sphere at the outer limits. I want to find the volume of the shell. If I find the volume of the shell times the density of copper will equal the mass of the water that's been displaced. Let's talk. So we got a bunch of stuff here, guys. Let me get rid of some stuff. I almost don't want to erase any of it, but I got to erase something, guys. The volume of the shell is this. So let's see what we got. We got all this in the notes, guys. Let me erase a good portion of this stuff, and then we'll just kind of hook around a little bit and see what we can do. How do you want to play this? My gut is telling me this. The volume of the shell, and here's the real strict way to do it. The volume of the shell is 4/3 pi r outer cubed minus 4/3 pi r inner cubed. The volume of the shell is 4/3 pi RO cubed minus RI cubed. And there's an invitation to a lot of stuff right there. Can play this a whole bunch of ways. Let's go back to the top. Let's find the inner one. Guys, this is the goal. We just found what the outer was. Let's find what the inner is. Outer minus inner gives us delta R, the thickness of the shell. Tell you what I'm going to do. Let's stay with the top. Bottom here was fine. There's a number of ways. There's ways you can play that too. But let me solve for the inner. Let me add 4/3 pi r sub I cubed on each side and subtract v shell on each side. What do you say? Let's just work with it. Let's multiply by 3 on each side and divide by 4 pi. We've been down this road before. Multiply by 3 on each side. Divide by 4 pi. True. Well, let me not do a square root. Cube root each side. The cube root of the cube root of Ri cubed is Ri, and this is whatever it is. The cube root of 4 pi Ro cubed minus 3 v shell plug them in, guys. Let's just remember what we discovered. We know 4 is 4. We know pi is pi. We know r sub 0 is 0.0. We know that right. Let me try one more. Okay. Obviously, this is where it's at. We got 4, we have pi, we have r sub 0. R sub 0 is 0.0612. You're going to cube it. Minus 3 times the v shell. The shell is 1.065 times 10 to the negative 4. And we did that earlier. See exactly where I did that. I know I did it, guys. Forgive me. I just want to make sure I'm not leaving you completely alone on this. Right, we got the V shell as well. So we got, as we said, we have 4, we have pi, we have 0.061210 rather. Guys, I'll tell you what, me saying this, let me just write it down so we don't have any kind of debate on the whole process. Sorry about that. Let me just make sure we can all agree on this. Now, there's a lot going on. You can almost, I don't know, whatever. You can play this a whole bunch of ways. You could take the 4 pi. You could take the 4 pi and go into here. You can take the 4 pi and go into there. If that's the case, it makes it a little easier. The 4 pi goes into 4 pi r0 cubed, ro cubed. 4 pi ro cubed divided by 4 pi. 4 pi ro cubed divided by 4 pi is just ro cubed minus 3 v shell over 4 pi cube root, and this is 0.0610 minus 3 times 1.065 times 10 to the negative 4 divided by the product 4 pi. Just that one is, not this one. Grind all that out, get the cube root. Ri that's very significant. Here's your Ri. It's a mess. It's a mess. How thick is this thing? Well, I don't. There it is. There's Ri. That right there, RO, our outer is 0.0610 meters. The other one is 0.0586 meters. When you do this, yeah, I mean, I think it's just 0.0024 at the end of the day on this. It's not too thick. Yeah, I think the way we had done it, I mean, is for some reason I had. Just seems like the answer should be a little bit different. It's not too. I don't think anybody's gonna make a big deal out of it, but I think the way we had done it was something had happened. This right here is a round off, a good round off. But when you actually, you take it a little more specifically, the delta R is. I don't think anybody's gonna make a big deal out of this, guys. But the delta R is 0.00238 meters, which is 2.38 meters, which is 2. Okay, let me go over here. 2.38. Yeah, to say that's a shell, it's definitely a shell. Man, it's not too thick of a shell, that's for sure. It's about, it's about a quarter of a centimeter thick. It's about a quarter of a centimeter thick when you're going to do it. But that is it. How that one's looking. So it's looking something like this. There's where you went. You had to get this thing under control. You did. You went right here. It's really 2.4 millimeters if you keep the number I got right there. I got a feeling I was being a little more precise in the process, for better or worse. It's not a big deal, guys. The big thing is don't be as close as you can be. One reason I'm right here actually doing this. You got that, you got that, you got this. And like I said, delta R is 2.38 millimeters. And that's for B. And that's what was going on right here. That's what we got right here. Not bad. Not bad at all. Let's talk about 68. It kind of comes back to what I said last time. In the Katz book, chapter 24, we talked about deformations and stuff like that, elongation, compression, bulk. We talked about the bulk modulus, the shear modulus, Young's modulus. Remember how we talked about compressive stress, tensile stress, and the like. And we talk about how volume can be deformed, how the length of something can be deformed, how shear can happen. Well, this is kind of going along those lines a little bit for problem number 68, rather. Okay, so let me see here, guys. Problem number 68. A device designed for undersea exploration is a solid sphere. Here we go again, that solid sphere, you guys. The bulk modulus is 120.0 times 10 to the 6th, times 10 to the 9th, rather, Pascal. So let's see here. For problem number 68, again, they're going with that sphere again, and it's copper, and it's, how did Yogi Berra say it? It's deja vu all over again, right? Number 68. A device designed for undersea exploration is a solid copper sphere. Now this one's solid copper sphere. Bulk modulus equals 120.0 times 10 to the 9th pascals with a radius of 2.5 meters. Find the change in volume of the copper sphere when the device is at a depth of 100 meters below the surface of the ocean. Now, you know what, this solid copper sphere thing, yeah, I think they're saying, if they're saying solid, it's not going to be a shell, like we said last time. So let's look at what I taught you guys the last time from chapter 14 of the Katz book, when we said how they all look like F equals Kx. They all look like Hooke's law within certain confined parameters, within certain limits. If things aren't excessive, F equals Kx looks a lot like what's going on with Young's modulus and the mathematics you use with Young's modulus, the mathematics you use with the shear modulus, and the mathematics you use with the bulk modulus. They all look like, there's all a linear relationship there, very similar to what goes on with Hooke's law. We talked about that last time in some detail. For problem number 68, what are they trying to say here? Well, they're trying to basically, at the end of the day here, they're saying, you know, just find the change in volume. Our assumption is there's going to be a change in volume and it's going to shrink. It's going to be smaller. It's going to be a negative. So when you look at this, let's just take the math that we got here, guys, and I'll see what I can say here. How did I do it? Okay, should be pretty straightforward. Okay, guys, so we're doing pretty good. Let me... Forgive me here, guys. Let me check my... Okay, I got a little bit of time. I want to make sure my mic doesn't run out, guys. And it's going a little bit longer than I wanted it to go, but I didn't want to start a new video. Since I'm starting these, I started these. I want to finish these as is. Okay, so let's do problem number 68 and be done with this. All right, there's a deformation that's going to take place. It's going to take place in a, as I said, kind of in a linear sense. It still doesn't make it that easy. You still have to watch it when you're doing this. And let's just see how this all will play out when we do it. Okay, they said what they said, guys. Let me just confirm. I've got my notes in conformity with what they're doing. We've talked about this. Let's keep talking. They are telling us that the radius of this thing was 2.5 meters. The bulk modulus is 120 times 10 to the 9th pascals. There was a unit for the bulk modulus. The depth, I'll call it h. Some people call it y. Just know what you're doing, whatever it is that you're going to do related to it. We know that pressure is bulk modulus delta volume over volume initial. We know that pressure final is pressure initial plus rho GH. Well, yeah, okay. Look, we don't really care about the atmospheric pressure because when you pull this thing out of the water, the atmospheric pressure is on it there as well, and the atmospheric pressure is still on it when you put it under the water, in addition to the fact that the water is also putting pressure on it. There's the atmospheric pressure plus the water. There's the atmospheric pressure from above plus the water putting its pressure on. But once you take it out of there, there's no more water pressure, but there's still atmospheric pressure. So it doesn't mean a whole lot. What do we mean? Well, I'll tell you what I'm going to do. If you're going to say delta P is going to be equal to the following. Why don't you subtract right here, subtract P0 on each side. Delta P is the change in pressure, is this guy. Well, we already said if you subtract P0, if you subtract P naught on each side, you've got rho GH. That's the change in pressure. You can treat P as delta P. The only way this works, guys, is if you really got a delta P there. So this gets a little touchy with the symbolism here. I'm sorry. P and delta P is the way to they're the same thing. P equals delta P. So if that's the case, stay with that, and then go delta P is B delta V over VI. Okay. All right, there's a lot going on here, guys. Let's get the a lot going on right, I guess you could say. At the end of the day, this rho has to be the rho of the fluid. You are immersing this in water. You're not immersing it in mercury. You're not immersing it in liquid gold. You're not immersing it in copper, liquid copper. You're not immersing it in liquid copper. You're immersing it in water. So this pertains to rho of H2O. This is G, that's H. Rho GH. So that's delta P. And we said at the end of that, you just call that P. Forgive all the gymnastics here, but that's a better way to write this thing is really delta P equals the change in P. It's a horse apiece. As long as you know what you're doing, you're okay. So just call the P delta P, and let's work with it. Delta P is the density. Now here we got to watch it. You got to use the ocean, and the density of the ocean. The density of the ocean is not 1,000. It's 1,025.18. G is 9.81, and the depth is 100. So that right there is all this. And this right here will be equal to something. Okay, so let's we'll figure out where we're going to put that. So I don't know. Let's leave that. Okay, let's just make sure my mic's working okay, guys. All right, so we have the delta P is this guy right here. We'll put that right there. Tell you what I'm going to do. That's good to know. Let's come back here. Let's solve for delta V. Delta V is VI delta P divided by B. Multiply both sides by VI and divide both sides by B. That's it. That's it. VI is 4/3 pi delta P. Man, we did that song and dance right here. We didn't fully do it, but we know what it is. Let's fully do it now. Take this, this, and this, and multiply them all together. And you get this. Probably a little more specific than I need to be as far as like how I take this thing, but I don't like to round off when I'm doing these. Divided by 12 times 10 to the 9th. It's a bit of a mess, but it's not hard. As long as you're careful, this shouldn't be bad. Just watch the numbers, watch where they go. This is going to be a volume reduction, guys. We know it's going to be a volume reduction. Why? Because there's more pressure on this thing 100 meters under the water than there is outside of the water. How much more pressure is there? Delta P more pressure, which is this, which is rho of the salt water times G times the depth at which it's under. Why did the atmospheric pressure not enter into it? Because it was in both places. I want the change in pressure. There's atmospheric pressure if I take this thing out and put it on the boat. If I take this thing out and put it on the ship, there's still atmospheric pressure around it. If I put it in the water, there's still atmospheric pressure around it, but there's something else around it that wasn't earlier, and that's the water. And that's how we got the delta P. That's why this was happening. This is rho GH plus PO. This is PO. Rho GH plus PO minus PO is just rho GH. This guy's PO. This guy's PO plus rho GH. Rho GH is the end of the story, guys. To get it there. Well, when you do this, it ain't much. It's pretty, it's a very dense object, and it's not very deep, but there is a reduction here. It's 5.49 times 10 to the negative 4 meters cubed. There is a volume reduction of this much. This is a volume reduction. This is a volume reduction. That's the end of it. And that's a volume reduction. You know it's got to be a volume reduction. What happens when you bring it out of the water? That same amount of change in volume is going to occur, but it's going to be a volume increase. It's going to be a volume increase, which means what? Which means it goes back to what it was before you had put it in the water, technically, assuming no permanent deformation takes place. Within small limits, this is okay. This stuff behaves like Hooke's law. F equals kx. A lot of it does. And that's what we said the last time we were together. All right, guys. Thank you for your time on this. And we'll definitely talk more. Take care. Thank you.